Good morning, everyone. Today I'll be presenting our work, Flash, Fast and Robust Framework for Privacy Preserving Machine Learning. This is a joint work done with my colleagues Megha and Ajit under the supervision of Arpita Patra. So I will be taking the roadmap as follows. First, I'll talk about what secure multi-party computation means. Then I'll talk about the different adversaries we tackle. Then I'll digress a little and talk about what machine learning as a service generally means. And then combining these three things, I'll come to our results. So let's start with what secure multi-party computation or MPC is. More formally, secure multi-party computation is where a set of parties have their private inputs and they wish to compute on some joint function of their inputs. So the goals for this MPC is the first one is correctness. That is, at the end of the computation, all the parties should indeed get the correct output. And second is privacy, that nothing more than the function output should be revealed. So in a more informal sense, any party should not be able to derive any additional information of some other party's input. Now we'll come to the adversarial model. So we divide the adversary based on behavior. That is, the first type of behavior is semi-honest, where the adversary follows the protocol as mentioned, but he tries to derive some additional information from the messages that he exchanged with the other parties. So imagine if I was one of the adversary, I would follow the protocol as mentioned, but I would sit with a pen and paper and try to derive some additional information from the message exchanges. Next is the malicious adversary. Here, the adversary can deviate arbitrarily from the protocol. So he can either follow the protocol steps if he wishes, otherwise he can completely do something else. The next is based on the number of corruptions. So the first type is honest majority. That is, if n parties are taking part in an MPC, we allow at most n by 2 minus 1 to be corrupt. That is, the number of honest parties in the MPC should be in majority. The next is dishonest majority setting, where in presence of n parties, we allow n minus 1 parties to be corrupt. So in our work, we look at the malicious setting and the honest majority setting. Now we further mention what degree of robustness is in terms of security notions. So the strongest notion is guaranteed output deliveries. That is basically an adversary cannot prevent the honest parties from getting the output. So the honest parties are always guaranteed to get the function output. The next weaker variant is if the adversary gets the output, then all the parties will get the output, else nobody will get the output. And the third and the weakest version is selective abort. That is where the adversary can selectively deprive the honest parties from getting the output. So what it means is basically at the end of the computation, the adversary will get the output for sure, but he can prevent some honest parties from getting the final output. In our case, we'll be looking at the strongest notion, which is the guaranteed output delivery. So now I'll digress a little and talk about what machine learning as a service is briefly. So nowadays, these giant tech companies like Microsoft, Google, Amazon provides servers on the cloud, which can be used by small labs or small companies in order for machine learning purposes like training, prediction, and other things. So using this service and the MPC that we have spoke of, we will come up with what this famously known area is called privacy preserving machine learning. Specifically in our setting, we looked at 4 servers in the cloud which interact with each other, which forms our MPC. And because we are in the honest majority setting, we can allow only one of the 4 servers to be corrupt. So on to my left, I have Alice, who is the model owner, and to my right, I have Bob, who is the client. So Alice has her trained model parameters, which she shares with the MPC, and Bob has his query, which he shares with the MPC. He wants the output to his query based on what Alice has shared her model parameter. So at the end of the MPC computation, he indeed gets the result for his query. And because of the properties of the MPC, we can guarantee that nothing about the model parameters is leaked to Bob, and nothing about the query or the result of Bob is leaked to Alice. So now, what are the tools that you require to build such a privacy-preserving machine learning setup? In our case, so first we'll talk about mirrored sharing. This is a new sharing format that helps us achieve guaranteed output delivery. Next is the by-convey primitive. This is the most crucial building block that help us build other protocols for privacy-preserving machine learning. Next is the multiplication protocol. As the name suggests, we want to multiply two ring elements. C is equal to A into B. The next one is extension of dot product protocol, where given two vectors, I would want to find the inner product or the dot product of these two vectors. The next come is fixed point truncation. As we know that when we multiply two ring elements, it's possible that the product might overflow from the range that we have defined. So in order to prevent such overflows, we perform truncation after a fixed set of multiplications. And there are many more that are mentioned in the paper, which you can have a look. So for the rest of the slides, I will be talking about our mirrored sharing format. Next, I'll talk about our by-convey primitive. Then we'll use these two to build our multiplication protocol and how we extend it to our dot product protocol. The ML algorithms that we are considering in our paper, first of all, we are looking at secure prediction. That is, given a query, I would want the output to my query based on the trained model parameters. And the algorithms that are under consideration in this paper are linear regression, logistic regression, deep neural network, and binarized neural network. So in this presentation, I'll talk about linear regression, which under the hood primarily just uses a dot product protocol. So let's finally come to our Flash framework. As I said, there are four parties. We call them as V1, V2, E1, and E2. V1 and V2 acts as our verifiers. E1 and E2 acts as our evaluators. So a function f that they want to compute is expressed as an arithmetic circuit, which is basically a composition of addition and multiplication gates. So we'll start with our mirrored sharing format. Let's say we have a value A and we want to create the shares of A. So what we do is we first add a random value, which we call as mask of A. We call this summation as log of A. Now, what I do, I take a hammer and hit it on the log and break it into two parts, such that when I add these logs, I indeed get back the log of A. Next, I go a little more crazy and I hit the hammer on the mask also, so that it breaks into two parts. Now we have four parts for this equation, and if anyone has these four parts, I can retrieve my value A from this. So now what I do is from these four parts, I give three parts to each party. So now if you look at V1 and V2, both of them have both the parts of the mask, but only one part of the log. Similarly, parties E1 and E2 have both the parts of the log, but they have only one part of the mask. And if you recall that we allow only one out of the four parties to be corrupt. So let's assume if E1 was corrupt, then he only has 3 out of the 4 shares with him. So for him, the fourth share is random. That means the underlying value A is also random for him. And also notice that whatever missing share that E1 doesn't have, in case of E1, he doesn't have MA2. So that MA2 is actually present by the rest of the 3 parties. So if any 2 parties, let's say E1 and E2 came together, then they could together construct back the underlying value A. This helps us later when we explain how guaranteed output delivery comes. So now let's come to addition protocol. I have color coded them in such a fashion that yellow color stands for shares that are already available, input shares, and blue color stands for the output shares that we need. So what I do is, given the input shares of A and B, I want to construct the shares of C. So I define my shares of C in such a fashion. I say MC1 is equal to MA1 plus MB1, MC2 is equal to MA2 plus MB2, and similarly for the case of lock 1 and for the case of lock C2. So now, why have I made it in this format? So if you look, let's say if you look at party V1, if you add the first column of V1, you will see that the summation of MA1 plus MB1 is indeed equal to MC1. Similarly, if you add the second column, you will indeed get MC2. And if you add the third column, you will get log of C1. So if you observe, that means party V1 doesn't have to interact with the remaining three parties to get the shares of C. So that means there is no communication required between the parties to compute the addition protocol. Similarly goes for the case of party E2, and you can pretty much extend it for the other two parties as well. So now let's come to our more important primitive, which I call as biconvey primitive. So here there are two senders S1 and S2, a helper H and a receiver R. Both the senders have a common values X. So what the biconvey primitive does is, both S1 and S2 feed their copies of X to the biconvey primitive. The helper H acts as the helper, as the name suggests, in the biconvey primitive. And finally, the receiver R receives the correct copy of X to him. So let's see what is actually happening under the hood. So both S1 and S2 sends their own copy of X to receiver R. So recall that one out of the four parties can be corrupt. So X1 may not even match with X2. So simultaneously, what S1 and S2 does is, they also send the commitments for their values to the helper H. So what is commitment? Primarily, I need two properties from a commitment. The first is the hiding property. That is, when the helper sees H of X1, he should not be able to decode what the underlying X1 value was. And secondly, I need is basically, given if X1 was not equal to X2, then the commitment on X1 and commitment on X2 will also not match. So given these two properties, now what happens is, receiver on his end checks if the copies of X1 that he received matches. If it matches, then he accepts that X and moves ahead and the primitive gets over. But what if X1 does not match with X2? So in that case, what receiver does is, he sends his internal randomness R, which is basically, you can imagine internal randomness to be, a helper H has three shares, 3 out of the 4 shares of any given value. And that missing share is possessed by all the remaining 3 parties. So what the receiver does is, he knows that one among S1, S2 is corrupt because X1 is not matching with X2. So he can safely trust helper H. And what he'll do is, he'll send all the missing shares that H does not have to him. And similarly, simultaneously, what the helper does is, helper checks if the commitments received from S1, S2 match. If they match, then he'll send the common commitment to receiver R. Receiver R will basically check if the one of the 2 copies which matches with the commitment. But what if the commitments also don't match for helper H? In this case, what will happen is, helper H will also send his internal randomness to receiver R. So even helper H knows that one among S1, S2 is corrupt. So he can safely trust receiver R and he can send the internal randomness to R. So after the exchange of internal randomness between H and R, now you can assume that both H and R are honest parties and they together act as a single trusted third party. So after the exchange of this internal randomness, each party can find the inputs of all the parties in clear, given that they have gotten all the shares, and finally compute the circuit output and send it back to the remaining parties. This way, we guarantee that the output is always delivered to all the parties. So given our biconvey primitive now, we'll come to our multiplication protocol, which becomes very simple. So given what we want to do is we want to compute the log of C. The log of C is defined as C plus mask of C. And due to correctness property, C is equal to AB. Now what I do is I substitute A as log of A minus mask of A. And similarly for the case of B, I basically open these brackets and rearrange them. And I write them as A1 plus A2 plus B1 plus B2. Now, why are these four terms important? Basically, each of these four terms are always available with two parties. So for example, if you look at A1, A1 is present with party V1 and party E1. Similarly, value A2 is present by party V1 and party E2. So, and the same can be said for B1 and B2. Now that given we have the copies of these values with two parties, we can easily call our biconvey primitive in this case. So now V1 and E1 input their value A1 to biconvey primitive, V2 acts as the helper, E2 gets A1. The same procedure follows for A2, where V1 and E2 feeds in A2 to the biconvey primitive, V2 acts as the helper, and E1 gets A2. The same procedure follows for B1, and a very similar procedure is followed for B2 as well. So and at the end of these biconvey primitive calls, we see that E1 and E2 both possess A1, B1, A2, B2. So both E1 and E2 can compute log of C. And now they'll hit a hammer and break the lock into two parts. Then they'll forward the second part of the lock to V2. So that's it. Essentially, the multiplication protocol has just reduced primarily to just some calls to biconvey primitive. Now let's see how the extension to dot product protocol works. So in this, if you do a few tweaks, you'll observe that the cost in our case for a dot product protocol is just equal to that of cost of one multiplication. Unlike the previous works, the previous ML frameworks that have been there, let's take the example of ABY3. They require D multiplications where D is the size of a vector. So if you imagine if I had two vectors of size 1 million, then the cost for the inner product or dot product of these two vectors would be equal to that of 1 million. Whereas in our case, the cost is independent of the vector size. So even if we had two vectors of 1 million, still our cost would be equal to one multiplication. So that helps us a lot in getting efficiency gains. So how does all of this look like in the benchmarking? So if you observe, we have given an throughput improvement over ABY3. So throughput is basically the number of queries that I can process in a second and minute respectively. So if you look at linear regression under the LAN setting, I have around 1300 times better. Inside the WAN network, I have around 120 times better. Similarly goes for logistic regression, we have much higher improvements, and for deep neural networks and binarized neural networks as follows. So thank you. That was it for this presentation. If you have any questions, please feel free to ask. And we have a full version which is available on ePrint, which you can have a look at.